Hello everyone, today I would like to present you with our GSU, Georgia State University's Nuclear Physics Group summer project, which is called S-Phoenix Hadronic Calorimeter Simulating Tau Testing. My name is Jinyu. So what is S-Phoenix? Well, S-Phoenix is a particle accelerator at Brookhaven National Lab, where this is a particle detector that is currently being built. So HCal is the hadronic calorimeter, which is part of the S-Phoenix that measures the energy of hadrons. Hadrons are like pions, protons, and neutrons, etc. So HCal composed of the scintillating plastic tiles, which scintillating just means light sensors. So at GSU, we focus on the HCal tau testing. Here's a right picture shows you the schematics of what each composition looks like. So we focus on testing the outer HCal and the inner HCals. So the HCal is the key for the precession jet measurements. Those are produced by Uniplus, which is a Russian-based company. At the bottom picture shows you the tau composition. The leftmost picture is the simulating plastics, and the middle one is the reflective coating, and the rightmost one is the bonded wavelength shifting fibers, which collect the photons. So the right picture is the cross-section of the HCal. In between the steel plate, we put scintillating plastic tiles. When hadrons hit the steels, the plastic scintillating tiles scintillates light, and the photons are picked by the fibers. So how it works? So this is the tau testing. The tau's performance measured by the response of the cosmic rays. So cosmic rays are high-energy particles from the outer space. Every second, there are thousands or millions of cosmic ray particles hitting us without our notice. So those are natural resources that we don't need to produce them. The cosmic rays strikes the scintillating plastics, which produce the photons. And then the fibers you can see here on the tiles collects the photons and then routes the photons to something called the silicon photomultipliers, or SIPM. So those are little chips that detects the photons right here, highlighted in red. And then those signals sent to something called CAN unit, which converts the analog signal to digital signal that computer can read. So after we have the data, so why do we do this? Because we want to have those tiles that we want to record the performance ratios for those tiles so that the Brookhaven National Lab scientists can sort the tiles to obtain the similarly performed tiles. So we have 12 different shapes for each tiles. The bottom picture shows you a top-down view for those 12 different shapes, and there are in total 5 layers of them, as the right picture shows you. Those are people sorting and assembling those tiles together in Brookhaven National Lab. So what does the testing stand look like? Well, here's the picture of it, and I'm putting the tiles inside this testing stand. So we test 8 tiles at a time along with 2 reference tiles on top and bottom, like a sandwich. For the outer HCal, we have each set of testing is 20 minutes. And for inner HCal, it's a little bit longer, which is 30 minutes. So we use the same reference tiles for each shape and every test so that we can have consistent data. So the test cosmic ray response results in something called Landau ADC distribution. So ADC stands for analog to digital conversion. On the right picture shows you x-axis as the analog to digital conversion, or ADC value. On the y-axis is how much time we get those ADC value, or the count. So from the graph, we extract the peak value here, which we call the most probable value, or MPV. And then we compare the MPV of the tested tile over the average MPV for 2 reference tiles, which we call the result as performance ratio, or PR. So we measure PR for each tiles, and the PR is the standard for sorting similarly performed tiles together. So here are our results so far. The left picture is the outer HCal PR distribution. We can see here, those are histograms, right? And we have binned to, the peak is at 1, which is good. And we also have a little small peak here, so that means we have sort of different performance ratios at different places. So our goal is to see a narrow distribution, which means we sort as many tiles as similarly performed as possible to optimize the final performance. And we have in total 7,760 entries for the outer HCal. We already finished the testing. And for the inner HCal here, we just have 1,812 entries. We are about 30% done, and hopefully by this summer 2021, we can finish all the inner HCal PR testing as well. So far so good. Most of those bins are located at 1, which we want to have as many similarly performed tiles as possible. So let's see our daily routine for students. So as students, we have a lot of boxing and unboxing routines. So we unboxing them while they ship from Russian, the company. And after our tile performance ratio testing, we put down our ratios in a piece of paper and then put those tiles back to the box and ship it back to Brookhaven National Lab. So during that process, we also learned how to use a root, which is high energy physics programming, use Python or C++ based, also Linux. So during that process, we learn about programming, we learn something about high energy nuclear physics, as well as a lot of communication skills during that process in that team. So thank you so much for listening. I'm happy to answer questions if you have them.